Hi. Thinking about sharing. Okay. So on the webpage, I have these handouts, the lecture notes. So we're going to just work through a problem. So I'll do a quick review and then we'll just kind of solve it. Yep. Yeah. And so mostly for them, the questions will kind of be for this first one, like, how do I set up this circuit to solve for like the final value? So yeah. Okay. Airplane. I can't get my AirPlay to work, so I'm going to just pick it up. Okay. Stop sharing. Okay, when we break up into groups, I'll encourage you guys online to kind of talk and work together. And so you guys can be your own group that is online. Hopefully I can get this to share correctly. Okay, so online I had a question about the assessment or for the RC and RL homework. And so the question is when you retake that assessment, do you have to provide the work? So you don't have to provide the work. Most of the time when you regenerate it or retake it, it should be a new problem. Some of those problems have answers and solutions to them, but some do not. And I'm trying to update it so they all have them. But last year when I created them, I created like 300 questions. So I do not have solutions to all of them yet. And so I will work on getting those solutions. But right now, a lot of them don't have solutions. So if you just try a new one, and that solution will be there. I'm also going to have an area that says Unit 1 practice problems. Those will have, again, some of those assessment type homework type practice problems. If you want to go work through some of those first and then go to the homework itself and then the quiz, that might be another way to practice. So if you don't need to supply your work for the assessments or the homework, but you will want to supply your solutions and your work for the quizzes, you'll get partial grade for the quizzes. For the homework, you won't get partial grade. You'll either get them all right or wrong. So that's more for you to work on your own with. Does that make sense? Okay. And any other questions? Did that answer the online? Okay, great. Okay. Make this as big as possible, but okay. It's only going to be as big as that. Okay. All right. So last time we talked about inductors and capacitors. Anyone willing to give a summary of the steps that were taken to solve the problem that we attempted? Anybody want to do it? Okay, Thomas.
You have to look at the circuit before the t equals 0. You need to see if it was open. I mean, if it was running for a long time, and then you need to do the switch after t equals 0. Look at that, and whether you're doing the RC or RL circuit, you need to find the current or voltage at the initial and final conditions. And then after you do that, you need to look at the equivalent resistance for the inductor capacitor. And you can calculate that.
Okay, so how? Find my, okay, here we go. I can find my pen. Okay, so you said the initial circuit. So this is my own quick summary steps. So finding the initial circuit. So with that initial circuit, you may or may not have a switch in there, and then you have an element in there. So how do you decide what to do with the switch, and how do you decide what to do with the element? Element meaning a capacitor or an inductor. So on there for the switch, you're going to look at when it says t equals 0 and which way the arrow is going. So if it's t equals 0, that means, and the arrow goes up, that means that the switch becomes open. If the arrow is going down, that means the switch is most likely getting closed. Okay, so that's how you determine where the switch is. So when you redraw, I typically say leave out the switch and the element. Draw that circuit and then determine what are you going to do with the switch and what are you going to do with the element. So switch position is going to be determined by location I can write on, by the arrow. So there'll be some arrow in there that will indicate, or it will say in words, you know, when the switch will be open or closed at t equals 0. So you're going to use that to determine what you do with the switch. Elements. So to determine the element, I put model of element. If you're a capacitor, what happens to the capacitor? It sat there for a really long time. Okay, so you make it an open. And if you have an inductor, what do you do? A short, correct. Do you guys remember why?
The capacitor is because the current on that is 0, right?
Yep. So that DVC dt is because that's 0. So current goes 0. So then you're an open. What about for the inductor? Why does that go to a short? So the change in current is 0, which puts the voltage to 0. So I told you to memorize 2 equations. What were those memories? Always says that. You're like, no.
Is the first one the C, or it's C times di dt? Is that one?
Yep. So this is going to be your IC. So the current through that capacitor is defined as the capacitance itself multiplied by the change in the voltage over time. Okay, what about inductor?
L times DI dt.
Correct. L D I L D T, and that's going to be the voltage change across it. So those were the two equations. Memorize or have on a piece of paper, easy to look at. Okay. All right. So then you can redraw the circuit like in the initial state. You're going to solve for the initial value. And then you're going to redraw it again at the final value, which was what Thomas said. So then redraw it again at the final. Again, determine what the switch is doing and what the element is doing. Then you're going to draw the final circuit and put where the element is, an A position and a B position. That's going to be determining then where you're going to take the pathway to find the equivalent RTH for that circuit. And that's how you find tau. So this is to help you find tau. You have to memorize again tau for the inductor and the capacitor. What is tau for a capacitor?
RC.
Correct. And for an inductor?
L divided by R.
Correct. So with this, you then have tau and you have an initial value and a final value, and then you can go back to the formula that we derived and you are able to plug in those values and write that general form equation. You guys ready to try it? Okay. All right.
Can you maybe wait a little bit?
Oh, sorry. Okay. While you're writing that down, yes. Okay, so go ahead and go to the next problem in the notes. I'll give you guys a moment. Introduce yourselves to your neighbors, work in groups of, small groups, so 3 to 4. And introduce yourselves if you don't know your neighbors that you're going to be working with, and go ahead and work on this next problem. And then you guys that are online, please work together. Okay, I'll mute us here so that you guys don't hear all of the rumbling, and then you guys can chat together. One thing to note is that you guys have the ability to annotate, and so I would suggest that you guys work together. Go ahead and annotate like on the figure itself. All right. So it looks like you guys have been discussing things online. So I'm going to go through the solution. Can you guys online hear me okay now? Okay, great. Actually, almost just.
Divided by. Yeah. That's the fact that we are.
Okay, so to solve this, you need to first find the initial circuit. So redraw, determine what are you going to do with the switch? What are you doing with the element? So those are the first things that you have to figure out. So in an initial one, this circuit has, so you look at it right before the switch changes. So I had a question as I was walking around. And so that will be your initial time, even though the switch is changing right at t equals 0, you do it right before t equals 0. So that means it's going to be open. And then after it's been sitting for a long time, the capacitor is open. And so you have no current in there. So that's going to be your initial value. For your final value, you're going to, oh, let's come up here and do this. So initial, you have this open, and then you have a dangling wire there. So the voltage across here has got to be zero because your current is 0. So VC equals 0 is your initial value. For your final value, this is now going to be closed, and this is still open because it's been sitting there. So I need to find the same voltage as V1. You can either see that this is a voltage divider and use the voltage divider equation, which I don't always recommend because people forget that voltage divider equation. The other way is to find the current going in that loop. It's a single loop, so it would be voltage, which would be 20 over 6K, and that would be the current going through this. So 20 over 6K is the current there. The other way you can do it is a node voltage equation. And so looking at this and just taking the node voltage equation, and I put the ground there. So this would be V1. So my equation would be V1 over 4K, or V1 minus 0. Again, it's minus anything in the branch. And then the other one is going to be V1 minus 20 over 2K. And then V1 is going to equal VC. And that ended up being 40 over 3. And that will be my final value. And then I need to find tau. And so for tau, I'm going to use tau as the final position, because remember the equation is at the final value, what is the ending of it? And so again, this is going to be shut. And now I'm going to replace the element in this case is the capacitor. I put A to B. And then this is only has independent sources. So when I find the RTH equivalent, I can remove the independent sources. So that allows me to make this become a short. And the equivalent comes in, pathway comes in here. And then at this node, it splits. So that has 2K in parallel with 4K. So and then it combines at the end and goes back to B. If you still want to color code, feel free to color code, whatever wires so that you can see that these are indeed in parallel with the colors are the same on the top and the colors are the same on the bottom. So that again, will be RTH. So that gives me 2K in parallel with 4K. And six, 8K squared over 6K. That is. Oops. I can add 6K. So that's 4/3. And this will have a K because it's K squared in the top and then only 1K on the bottom. And then tau then is RTH times C. So 4/3 K times 2 micro. What's micro? Okay, good. 10 to the minus 6. And so 8/3, 10 to the third times 10 to the minus 6 is 8/3, 10 to the minus 3. And this will be in seconds. And then the general form is going to be the final value, which was 40/3, plus the initial, which was 0, 40/3 for your final, e to the minus t over 8/3 times 10 to the minus 3. And that's going to be in volts. Hey, questions? Yes.
Would it be okay if we just use decimals instead of fractions?
Yeah. Yeah, so I had one question. Somebody asked me like, as far as what am I looking for? So on your quizzes or your exams, a lot of times I'll say add a specific time t, plug that into your equation you got, and then you'll have a choice of, put that value in. And so that way it makes it easy to do auto grading if you are correct. If you're not correct, you'll still get partial points for this because you'll submit this work and it will show, oh, you just did a math error in actually calculating, when t was equal to that value. And you'll get full credit if the equation is correct. So that was what the question came up. Okay, so do make sure to keep all your work, make sure you're able and ready to kind of submit that at the time for the quizzes and the exams. Okay, other questions?
There was one in the Zoom chat.
Oh, thank you. Use the voltage divider with the circuit. So if you don't know that that's a voltage divider, node voltage works. So I tend to say, just don't rely on the equations for voltage divider and current dividers, because you'll probably forget them. And so node voltage always works. And so just look at the node you're looking for, write the equation set for that one. And then if it has another node, then write the equation sets for that one and then solve them backwards. So in this case, I didn't need to know that it's a voltage divider. And if I don't see that it's a voltage divider, that way I can just always write those node voltage equations. And you guys have handy online tools or calculators that do your matrix too. So if you set up your set of equations, you can go ahead and use those. All right, other questions? Okay. All right, let's do another one. So this will be a inductor. And in this one, you want to find IL of T. So break up into your small groups again.
Oh, yes, yeah, yeah. So if it's. Alright. What happens when it's nothing it's still not. I like these ones here. Yeah, I think initially it's. Yeah.
Oh, wait, no, Venom.
So it becomes short. My stuff. When you make those in parallel, they're all very little. Wait.
Yeah, we can use that. Simple use that.
That's all the resistance. Oh, great. You want to figure out this? Yeah.
Evaluating. To be honest, I think yeah.
Wait, yeah.
I like it. So I'll show you how I always. Yeah, dude, and then. super good. Yeah, like how I was this. So you're looking for. And then, yeah, we're going to have. So, yeah, just take the from that. And then I know. Oh, something different. No, yeah, you just have to make. It still gives you the rating. Yeah. Yeah. But that's another reason, like, yeah.
Now we know. Yeah. Yeah. Yeah.
But so I would say like these then you I have to do it one at a time. I just do it one at a time. A lot.
Yeah.
All right, so for the initial value, where's the switch? Okay, so t equals 0 with the arrow pointing down as it's closed at t equals 0. So you do it right before the switch changes, so it will be open. So I leave this open. And what do I do with the inductor? Short it, correct. So short the inductor. And then I want to find this IL of t. I can do node voltage here and put this as ground if I want, and I don't see it right away. So Vx over 3.6K, it'd be Vx minus 0. And then Vx minus 0 over 7.2K. I solve this and I see, yeah, Vx is 0, so IL has to be 0. If I see it, I can just say, well, there's no sources there, so there's no way it can have any current there. So IL has to be 0. But if you don't see it, mathematically, you can solve it still and find that Vx is 0, so IL would be 0. So this is my initial value. Now I need to determine, what do I do? I redraw the circuit, which I copied. But what do I do with the switch now? Okay, so good. So I close the switch. And what do I do with the inductor? Short it again. It's been sitting there for a long time in the final position. And now I need to find IL here. So you could notice that this is a current divider, but again, I don't recommend memorizing those equations all the time. So just do node voltage would be again recommended. So the top node is all the same. So I could label that some value. I'm going to call it V1. And then I want to provide a ground if there's not one in there. So I want to pick the ground. To me, I always like to put it on the bottom because it visually looks better to me. So I'll try and do that. Or the other location you want to put the ground, if it's not in there, is the one that has the most branches going off of it. So in this case, it's also on the bottom. Okay, so node voltage, it's going to be all of the currents going out from the node in that direction. And I go from the positive side, which is going to be, arrow is always the negative side. And I start at the positive and then I subtract off everything else in the branch. So V1 or current source is going to be the first one. So that current's defined as going in. So I'm going to do a minus 2.4 and milli is what? Minus 3, thank you. And then the next branch with the 1.2K is going to be V1 minus 0 over 1.2K. And then the next branch is going to be V1 minus 0 over 3.6K. And then V1 minus 0 over 7.2K. So there is my equation. I can combine all of the V1 components. And then I can take the negative over to the other side, 2.4. Move this bar, I guess I can't. I can find a value for this and then divide it over 2.4. And that ends up giving me a value for Vx, so 2.4 milli. And once I get V1 to find IL, which is what I need for the final, I just take the voltage over the resistance in that branch. So that will be again V1 over 7.2K. And that ends up being 4/15 milliamps. And you can write that as a decimal if you like the decimal better. And this is going to be my final value. Did you guys get that? Okay, got some thumbs up. Yes, no, it's awesome. Okay. Okay, great. So it looks like you guys are all on the right track. If you made an error somewhere, try to figure out where you made your error. Again, memorizing those equations for the voltage and current divider sometimes gives you the error. So doing the actual math is more recommended. Last step, yes, question.
I know in this problem, you can just combine all the resistors in parallel.
Uh-huh.
But in the case that you couldn't, would we still be able to combine like the 1.2 and 3.6 and then do the same node voltage that way?
Yep. So yeah, to simplify this, you could combine, and you could find the voltage V1 that way too. Just combine all those resistors, 3 resistors in parallel, and then 2.4 milli times that resistance is going to give you V1. And so you could find V1 that way, then V1 over the 7.2K will give you the current in that particular branch that you want. So you can do it that way. You could, if you needed to just combine a couple resistors, you could combine the couple resistors to simplify that portion of it. And I do recommend try to simplify it as often as you can where you can. All right, final value for tau is the only other thing we need to know now. So again, the final circuit, so this one will be closed again. And then here I leave out the element and I put where A and B on the outside element of where that element is. So now I want to find the pathway from A back to B as my RTH. So what happens with the current source? Correct. It goes to an open. Remember, when you put I equals 0, that opens up, no current flowing. So this becomes an open. So I'm going to actually just kind of move these wires out. So this is the pathway that I want to take. If I start at A, and I recommend, some of you may like this method, some may not. So whatever method works for you to visualize, are these in resistors in parallel or series? I like to physically put my pen down on A and I move it as I go. And then once it branches out and has a 2 pathways, that's where it's in parallel. If they join back together, then they come as the rest of it as a sum. So if I was to put my pencil down and I can see like, yes, there's going to be a split there. So, oh, that's not what I wanted. So here I can see that there's going to be a split. So those 2 are in parallel. And then they join. And then they join back together again. n to 1. So this is going to be an RTH is 1.2K in parallel with 3.6K plus 7.2K. So that's how I get the RTH there. And remember, for the parallel form, you can write this as either this form or you can write it as 1 over 1.2K plus 1 over 3.6K, whatever way you like to write it. And that ends up being 8.1K. So now I can combine all of them and write the equation for IL of T. So my final value, which was 415 milli, my initial was 0 minus 415 milli, e to the minus t, and then, oh, I didn't finish writing tau, sorry. So tau is what for an inductor? Correct. And so L was 81 millihenry. And so 81 milli over 8.1K. And I didn't write that out, so I'm gonna have to write it this way. 81 milli over 8.1K. And this will be in amps. And that is my final equation for IL of T. All right, questions? Okay, this is what your homework is for next week. So on Thursday, these will be due, an RC and RL circuits like these. So work through some more problems. I think we have time for one more. So let's go ahead and work. I'll have you guys kind of help me because we only have 10 more minutes. So, well, why don't you guys take like 3-4 minutes,
All right.
work on your own, and then we'll go through the solution.
Oh, wait, never mind. Oh, I see. So, before it's clear, we should basically be able to work out.
All right, so for the initial, what's your switch gonna do?
Stay close.
Okay, so for the initial, we closed. And then what do we do with the inductor? Closed. Okay. So again, I like to put this on the ground. And then I'm gonna just call this Vx. Currents go out from there, so a minus 60 micro, Vx over 10K, Vx over 10K. And I can solve this for Vx. So this ends up being 30 micro. Or wait, no, that's the current. Vx, I don't know what this is. Okay, and then IL is Vx over 10K. And this ends up being 30 microamps. So this will be my initial value. Final, what happens to the switch? Okay, so I'm going to leave it open. So I'll put that on both. And then for this final one, what do I do with the inductor? Short it, correct. And then I can do node voltage here again, or I can just see that there's no sources. That's got to be 0. So my final value will be 0. Here I replace the inductor with A to B. And what is my RTH going to be? Say it louder. Can somebody say it? It will be 20K, 10K plus 10K. So those are in series. And then tau is L, which was 3 milli over 20K. And so my final equation for IL is going to be 0 plus 30 micro minus 0, e to the minus t. This is I actually wrote this one out, 150 nanoseconds. And this again will be in amps. And there's my solution. Hopefully these are starting to feel a little bit more comfortable about going through them. So this is the focus for this week, is to work on these. Labs will start on Monday. So if you're in a Monday section, lab will be held on Monday, and then all the other ones will be held. And then Monday's lab, so then there'll be tail lab. Okay. All right, any questions? Okay. See you guys next week. All right, any questions online? You guys.